All right, so our speaker is Chun. If you can go up, I will read. There you go. Who will present a paper now? Instead of going deep, he will talk about wide neural networks and see what their effects are. Go ahead, Chun.
Okay, thank you, Dr. Vitali. So the paper I'm investigating is wide neural networks of any depth evolve as linear models under gradient descent. And I have an outline for the main topics I'm going to go through. Yeah, and so first, like why we investigate the width of a neural network is the motivation. Because like the training dynamics of current machine learning models are always challenging to explain. And this is partially because of the complex systems and over parameterized models that we build, which result in a very high dimensional non-convex loss landscape. Sorry about it. That is hard to analyze the learning dynamics. And also with different optimizing methods such as gradient descent or more complicated such as those with momentum, it's becoming even harder to track the training dynamics. So an approach that the researchers take is to start from an infinite width perspective. So by assuming that the width grows larger and larger and ultimately to infinity, there would be some simplifications in the theory part that leads to better understanding of the learning dynamics. Also, greater width is a tool for better generalization, so it's also preferred. And we will talk about the remaining concepts later. So main contributions involve parameter space dynamics, analytics, and output distribution dynamics. But I feel the parameter space dynamics is a byproduct of the explanation of the output distribution dynamics, which is how the output of each layer of a neural network will evolve in time. And that's the key topic that the researchers are interested in this paper. So in short, the researchers try to form a time-dependent evolution of Gaussian processes for each layer of the network during training. And also they use a neural tangent kernel for explaining, the output dynamics. And they also claim that under a certain threshold learning rate, those networks with infinite width can share the same learning dynamics of such of a linearized system. So when the system starts to learn linearly from its initialization. Yeah, and we ultimately provide some experimental support. So some basic knowledges first to grasp is a kernel function, which is essentially a non-parametric instance-based algorithm that takes two features in this case. So phi psi x and psi x prime. We measure the similarity of those two quantities, and we investigate how change in one quantity will affect the state of the another. We can use this kernel-based approach to predict a new unknown sample based on all the non-samples, observed samples with a conditional probability. We will go through some concept of a Gaussian process. Is given a collection of data points, we assume those data points form a multivariate Gaussian distribution defined by a mean mu and a covariance matrix sigma, where each entry of the covariance matrix is a kernel function of data point x and data point x prime. And yeah, so now we get to the neural networks, and some notations that we want to specify are listed here. It's a little complicated, so like we can.
Chantal, can I ask you? So x and x prime are two members of this data set, or no?
Yeah, so x and x prime are two input points, so two data points that we are
data
given
points
with.
in that list that you provided later, where you had listed all of the data points. So it's one of the both of them are two different data input data, right?
Yeah, two different.
And then psi of x is what?
Psi of x is let's say you have a model, you forward pass your input x into the model and you get a feature. So like phi x is the output of that.
Okay, so it's an output.
Model.
So like y of x from the previous talk.
Yeah. Essentially, it's some function over the two outputs of a same model, but on two different data points.
Yes.
Okay. And so some notations is I feel like we just need to take care of the bottom ones, in that the the pre-activation vector of the L+1 layer is the the forward propagation of the post-activation of the else layer. And also note here we have a scaling factor of 1 over square root n L, where n of L is the width of the else layer. So this is arbitrary in here, but it is referred to as the neural tangent kernel parametrization. It's a parametrization that says, the scaling of the previous post activation is inversely proportional to the width of the last layer.
Sorry, isn't the purpose of this is just to make sure that all weights are of order 1?
All weights of
order 1. So this is like, if you had if you have this weights, this WL transpose, if you had all the weights of order 1, then you had n incoming connections to the next neuron. And so if all of them are of order 1, then on average they will be they will be scaling x squared of n. And then you just remove this trivial scaling so that everything stays of order 1.
Yeah, you are saying it's a normalization in the
it's a normalization under assumption that the weights, you just don't want to work with weights that are too small or too young. That's my understanding, unless
that you can understand like that, but it's like in the paper it's just referred to as this specific parametrization. It's a non-standard way of propagation, but it's arbitrary.
Right, but it's fine. This just rescales the definition of W's of the weights, and that's all.
It is. So next we move to the concept of neural tangent kernel that's beneficial to our investigation. So here, instead of like the product or a function over two features, here we define the let me start again. So the empirical loss function here is L, which is a function over your model output and your labels Y. And then if we do the derivatives on the parameters, it becomes the next expression here. And then what we are interested in is the dynamics of our parameters. So we want to find out what d theta dt is. And if we are using gradient descent, we use the negative gradient of the loss over the parameters. And we assume that time update is infinitesimal. So like in a very short time update, we get this gradient descent and we equalize the two terms. So we get a time evolution of the parameters, which is equal to minus the loss gradient. And then what we're interested in as well is the output time evolution. So d fx over dt. So here fx means the output of the model in the final layer, and we equate it. We use the chain rule, and we have this intermediate term, which is the product of the output derivative with respect to parameter. It's let's say it's a dot product with itself. So that we refer to as the neural tangent kernel, and we will later see it will be useful in our computation of the output dynamics.
Sorry, on the previous slide. So in this upper equation, that's the middle term, you use d theta, where you're thinking that it's a single parameter theta, and later you do gradient with respect to theta when you think that theta has many variables. So I think this is the same thing, right? So it probably
theta is a collection of variables, yeah.
Right. So then it should be gradient on the left as well, right? So it should. So you should be summing all variables, and so it's not the single. So it's not just d theta d. It's a vector, right? Theta is
right. So yeah. So probably should use the, the gradient sign there.
Right. Exactly. On the left. Exactly. That's my point.
Okay.
Right.
Okay. I would.
But then the second one makes sense because the second one is just you carrying through the same term to the right, and then
here the purpose is just to show the chain rule process.
And then the second d theta dt comes from the previous slide where you just wrote the stochastic.
Yeah, that's right.
Yeah,
that's
exactly.
Right. That's why we get the product term. Yeah, so
that's right.
Yeah. And we refer to that product term as the neural tangent kernel. Later we will see why it's useful in our modeling of the system as a linear system. Yeah, so here we introduce another concept of a neural network gradient process. Basically, the core idea is that if we start from a certain initialization and we have this multivariate Gaussian distribution in our first layer output, then we can use induction to get the result that we can have a Gaussian process for each of the inputs of each of our layers in the network. So the output of each layer of our network becomes a Gaussian process, and in the end, the output becomes a Gaussian, a multivariate Gaussian. And each of those output function has a covariance matrix. So here we derive the covariance matrix for the output of the first layer. Here, it is specially noted that we use the initialization that's bounded, that's specified in the blue bounding box here. So it is a specific initialization, but in the end, we get the result that the first layer has a covariance matrix and is a Gaussian distribution. And also worth noting here that the weight and bias parameters are initialized IID. And from that first case, then we can propagate from the else layer to the L+1 layer using induction. And here we see it's some complicated mess, but like in the end, if we plug in the propagation relationship between the else layer and L+1 layer, we find in the end we can also get a covariance matrix that has this form. Maybe I should use a pen.
So sorry, the one thing I'm missing when you do the propagation, where is your activation function? Because I see only the linear.
Yeah, here it is. Yeah, so let me get a pen. Is there a maybe? Oh, is this a pen? Okay, so like here, the sigma is the activation. Yeah, so from the else layer to the L+1 layer, you first go through the activations, and that's why this thing becomes this.
I see.
Yeah, the math is a little bit complicated in my slides, but we can later check on it. Yeah. And so here we also take the limit that the width of a certain layer L goes to infinity, and in that case, if we do the the expected value of the product, then we can assume a output function that's a Gaussian distribution with mean 0 and the covariance matrix lambda specified in below. So anyway, the core of this two slides is that a neural network feed-forward model can be modeled as separate a sequence of Gaussian processes for each of its layers.
Okay, maybe once again, what do you call a Gaussian process? So you take the input variable. Yeah, so maybe.
Yeah, a Gaussian process is we model a multivariate Gaussian distribution for the output of each of our layer. Yeah.
Okay, but that's an assumption of Gaussianity. You want to model a transition from the previous layer to the next layer.
Yeah, it's just
are you modeling the transition as a Gaussian, like, you know?
Not the transition is a Gaussian, but the output of the transition is a Gaussian. Yeah.
So if you look at the given state of some layer over the entire epoch, then you obtain some kind of a Gaussian distribution of the multivariate Gaussian over the states of neurons. Is that your statement?
Yeah. We just care about the output states of each layer, and we have this induction, and in the end we say they are all Gaussian distributions. So we say in the end the whole flow is the whole feed-forward function, the whole transition is a Gaussian process. Yeah.
But it's important. The transition between layer to layer is a Gaussian. So what is the Gaussian random variable? Is the transition the difference between the states, or just look at the given layer and then it's going to be a Gaussian distribution?
Just look at the given layer's output.
So, but then it's not a Gaussian process; it's just a Gaussian state, like normal distribution.
Well, it transits from the first layer to the end, right? So
maybe the mean depends on the state of the previous layer. So I mean, it's hard to see.
Anyway, we are interested in the output dynamics of each layer, and we claim that each of these layers is a Gaussian distribution, and the whole transition is a Gaussian process. Yeah, that's the point here. And also, let me go to. So that's one way of modeling of the transition from the first to last layer of a neural network. And we also have another tool, which is the neural tangent kernel that we discussed about. It's a similar formulation to the previous slides, but here you see, like in the first layer, we equate the Gaussian kernel to the covariance of two data points. And then we again use the induction from the else layer to the L+1 layer. And we can skip the process and we can focus on the last part, where we assume, in the case that we assume the else layer has a deterministic limit for its neural tangent kernel, we also get a new limit for the neural tangent kernel for our L+1 layer. So as you can see here, the K infinite, here is the assumed NTK limit of the previous layer, and we have the term here to claim that the L+1 layer has a new deterministic Gaussian. So in the end, how do I go back? So in the end, here are the two claims. If we have a deterministic initialization, our Gaussian kernel will be our NTK kernel will be irrelevant to the initialization and only determined by the model architecture, and it will stay constant during training. So this K function that stays constant will give us a converging limit for each of our layers and even the final layer. So it is neutral for modeling the feed-forward network. Here are some visualization. So like if we want to model the relationship between the input on the x-axis and the functional output on the y-axis, we see from the animation is across the time evolution. We see from different initializations. Here, in different colors, we converge to a similar parameter space after a few epochs. And here, the claim is that the wider the network is, the larger the width is, the more similar the different initializations finally look like. And this is only in the domain of gradient descent.
So what are the individual lines here?
Different initializations, different.
And then those initializations for weights, right?
For weights and biases, yes.
Okay, and then what is one line represents when you go to it? It's like a regression model here.
So the two red, yeah, it's a regression model. It uses MSE loss for gradient descent, and and the two only data points here are the red dots.
I see. You only have two data points, and you're trying to from them learn. I see.
Yeah. And the claim here is like with a larger width, you see the ending results to be similar to each other. So like different initialization finally results in the same learning dynamics.
I see. So the point is, in the limit of NT being infinite, the system will be just producing the very same result regardless of the initial conditions of the weights.
That's correct.
You'll be just getting exactly the same.
That's correct. Like the neural tangent kernel we said about, it will
dominate the kernel.
It will.
I see.
It will stay constant during training, and it will dominate in the end. And it will be irrelevant to the initializations.
I see.
Yeah. So here is another great discovery is like if we investigated the time evolution.
There is a question now, so I don't know if you want to answer it now or later.
Yeah.
So Nicola, you can just speak up and say.
Oh, okay.
Okay, I probably just repeated what you said, but is the claim that as the width of each layer tends to infinity, all the networks degenerate to a linear network, like to a linear model? Is that the claim?
Yes.
Okay. So it's a simple claim. I'm trying to see if I'm missing something. Thank you.
Yeah, I will later specify why it is the case in my next two slides. So
okay.
Yeah, here we investigate the time evolution, the time derivative of the output function of our model. And again, we use the neural tangent kernel to represent the product term. And this term, I want to reiterate that it comes from the chain rule that we showed in the beginning. df dt is equal to df d theta times d theta dt. So after we replace the Gaussian the neural tangent kernel in here, and we knew from the infinite width that our neural tangent kernel is going to be deterministic to k infinity, so we can replace it here, and now we have this expression, and we leave it here, and we try to consider a linear system, a first order Taylor expansion of the output function. And we just take the first two terms so that it becomes linear. And we have the output function value at its initialization plus this derivative term times the difference between theta t and theta 0. So it is just, it now becomes a linear system. And if we investigate further, we plug in theta t minus theta 0 to be the negative gradient, assuming that the time step is infinitesimal. And also we plug in, we have from the previous relationship, we plug in the derivative of theta of the output function. Then we can equate this expression on the left, which is df dt, to the same expression we had for our infinite width network. So and after replacing ntk function of theta 0 to k infinity, we get the same expression with our infinite width networks. So we finally can give the proof that the infinite width networks have a learning dynamics that's the same as those governed by a linearized model. Yeah. And here's an example of a specific loss. So we investigate the MSE loss, and we plug in the loss derivative with respect to output in here, f theta minus y. And so we solve this ODE differential equation, and we just use our ordinary differential equation knowledge to get the solution that the difference between that our g theta, which is f theta minus y, will be this expression, and f theta becomes a function of the f theta at time 0, and another term with respect to y, our labels. So like it is reasonable that when it goes to infinite time, the first term will become 0, the second term will dominate, that our model will learn to predict our inputs as our labels. So it's an effective learning system. And we also evolve the use of the stable tangent NTK kernel value here. And so here are some of the experiments. So we see like it is a similar formulation of the previous learning dynamic graph we have shown. We have 2 data points to learn on, and we use gradient descent. And the different colored curves here are different initializations. And this is the visualization from t equals 0 to t equals a large number. And we see the 3 modeling of the feed-forward propagation of the neural networks, which is the neural network itself, the NN Gaussian process, and involving the use of neural tangent kernel. All 3 analytics, we show the 5th to 95th percentile data, and we show they converge to similar curves, and that the learning dynamics modeled by these 3 tools are basically the same. And here we compare the neural networks themselves to their linearized version. Their linearized version means using the k infinity, the constant NTK value we have talked about, and we see the linearized models curves to be shown in the dashes, while the neural networks themselves to be in the solid lines, and we see the 2 to match in the output dynamics, the parameter space dynamics, the learning dynamics, and also an additional observation is that if we use the empirical kernel theta tilde instead of the analytic infinite width, so the ideal value of NTK kernel, we can get a more accurate approximation of the difference between the model's output and the linear model's output. And here are some similar plots. Here we have the test and train output dynamics, and also test and train learning dynamics, the loss and accuracy. And we see the neural networks with infinite width or large width to behave similarly to linearized models in those cases. Yeah, and here are some references, and that's the end of my talk. Yeah. Thank you.
Perfect. Thank you. Thank you very much, Chanta.
Yeah, thank you.
Questions? I see a thumb up. All right, there are no questions. Let me thank you again, and let me stop recording.
Okay, thank you.